Worked on and might have questions about. Let's see what looks good and what doesn't look good as far as the test is concerned. So if we're looking at this, maybe I could copy and paste some of these. Suppose we're looking at these problems. Would there be anything wrong with them? If you like polynomials, open intervals where a function is concave up or concave down, we like that. Take a couple derivatives. Find the zeros of the second derivative, construct a sign graph for f double prime, and then based on that you can tell the intervals where the graph is concave up, the intervals where the graph is concave down, and any inflection points. If it's continuous and there's a point on the graph where the concavity changes, you want to give both the x and y coordinates of that point for the inflection point. That one looks pretty good. Problem 2, I'm thinking it might not have any inflection points. I can imagine that it would likely be concave up a good ways and concave down a good ways, but the one second order critical number, namely 3, where the vertical asymptote occurs, is not a point where the function is continuous, so it would not be an inflection point. 3, second derivative test. Now, second derivative test is used to analyze zeros. Well, it's used to analyze first order critical numbers. Those can be zeros of the first derivative, or they can be places where the first derivative does not exist, points basically of non-differentiability. So for polynomials, that's kind of nice. It's just, I think the details of how to apply the second derivative test are going to be what's important here. Already got it here in the worksheet. So if we wanted to consider the second one there, negative 3x to the 5th plus 5x cubed, maybe take just that one, move it down there, take a couple derivatives. Let's just see how this would work. F prime of x equals negative 15x to the 4th plus 15x squared. F double prime, wait on F double prime a while. Is this okay for the first derivative? Do that okay? Set it equal to 0 so we can come up with the critical numbers. No points of non-differentiability for this polynomial, but maybe a couple, maybe more, where it actually does equal 0. So x squared. Now how about negative 15x squared? Factor that out. And so we'll have x squared minus 1. Look okay? There is the first derivative. Now maybe the negative 15x squared equals 0. Maybe, I'm skipping a step, huh? Let's factor it. Negative 15x squared times x plus 1 times x minus 1 equals 0. So maybe x plus 1 equals 0, maybe x minus 1 equals 0. So 3 first order critical numbers, 0, negative 1, and 1. Arrange those on a... No, don't. Let's not arrange those on a number line, because if we're going to apply the first derivative test, we would consider a sign graph for f prime. The advantage of applying the second derivative test is that we don't have to do that. So I'm going to skip the sign graph for f prime and go directly to f double prime. F double prime of x equals negative 60 x cubed plus 30x. That look okay for f double prime of x. We evaluate the second derivative at each of the first order critical numbers, looking to see, is it a relative maximum, relative minimum, or is it one of those cases where the test is inconclusive? That can happen. F double prime of 0. Should have saved that one for last probably. F double prime of 0. No, I'll tell you what, I'm going to save it for last, sorry. Let's do f double prime of negative 1. F double prime of negative 1 is negative 60 times negative 1 cubed plus 30 times negative 1. f double prime of negative 1 is 60 minus 30, which is 30, which is positive. So here's what we're saying in applying the second derivative test. F prime of negative 1 is 0. That means horizontal tangent line to the curve. F double prime of negative 1 is positive. That means concave up. So if there's a horizontal tangent line and the graph is concave up, are we thinking relative minimum, relative maximum, or who knows? Looks like relative minimum. So you would say F has a relative minimum at x equals negative 1 according to the second derivative test. F double prime of 1 is negative 60 times 1 cubed plus 30 times 1. F double prime of 1 is negative 60 plus 30, which is negative 30, which is negative. So we have a situation where f prime of 1 is 0, horizontal tangent line. F double prime of 1 is negative, so it's concave down. So f has a relative maximum at x equals positive 1. And then we apply the second derivative test at 0. And let's see, probably should have done that one first. I can grab most of this and shrink it. I will. So we do this. F double prime of 0 equals negative 60 times 0 cubed plus 30 times 0 equals 0 plus 0, which is 0. So here's what we know. We know there's a horizontal tangent line at 0. But we don't know whether the graph is concave up or concave down, or maybe a little both, in an open interval containing 0. We don't know. It might be one or the other. It might be that there's a relative minimum at 0. It might be that there's a relative maximum at 0. We want to be really careful not to say that the function does not have a relative extremum at 0. We look at the graph and maybe figure it out. More seriously, we should look at the first derivative test to answer the question conclusively. But the second derivative test is inconclusive on this matter, and that's the answer we want to give. You don't want to say none. You want to say the second derivative test is inconclusive. Because probably the way I'll ask it is, what information does the second derivative test give you? And you could say no information because it's inconclusive, rather than is there a relative extremum. The second derivative test is inconclusive at x equals 0. Really good example. If I can come up with an example that does all of this that this example does, that would be a fantastic winner, chicken dinner test question. That would be fantastic. I hope I can do that.
Something like 1 or 2?
Well, yeah, 1 and 2 look okay also. Yeah. But I felt like 4 and 3 also I think looks similar and would also be well worth our attention. So all those look pretty good from section 4.4. How about 4.6? Some of you know what to expect here. You know what to expect. Expect something like a third or maybe a fourth degree polynomial like this. And I will give, and what you want to do is find the zeros, basically set the function itself equal to 0 and solve for t. Find the numbers that make the original function equal to 0. Take the derivative. Find the zeros of the derivative. Find the second derivative. The zeros of the second derivative. And then take all of those, the zeros the zeros of the first derivative and the zeros of the second derivative, and arrange them in order from left to right along the number line. Let's say starting with t equals 0. If there are any negative ones, we'll disregard those because we want to consider what's happening moving forward in time. Put those on the number line, and that will partition the number line into little intervals, like a couple of 3 problems that we did in class. And on each interval, I'm going to want to know the particle. Is it on the positive side of the origin? Is it on the negative side of the origin? For that, you ask yourself, is s of t positive or negative? You can see, is the graph above the x-axis or below the x-axis? Then I'm going to want to know, is it headed in the positive direction or the negative direction? And that's simply the sign of v prime, or sorry, the sign of v of t. That's s prime of t. You look at the graph, is the graph rising or is it falling? You can tell the direction that it's headed. And then you look at the sign of v of t and the sign of a of t. If they're the same, it's speeding up. If they're opposite of each other, it's slowing down. So I'm going to want to know, is it speeding up or slowing down on that interval? In most cases, you can get that by inspecting the graph for polynomials. You usually can, but you want to go through the algebra to find the zeros of s of t, v of t, and a of t. So evidently good examples of polynomial functions. The t to the 4th minus 4t plus 2 is probably a good one. 3 cosine pi over 2t. I think that'd be a great homework question. I don't know if it's a great test question since I didn't do a trig question like that in class. So I would say don't worry about the second one. Look for a 3rd or 4th degree polynomial and expect to be able to do this with a 3rd or 4th degree polynomial. Not a 1st degree polynomial. That's not very interesting. That looks like a good one. So 3 out of 5 of these. Was it 1, 3, and 5? Are those the ones? 1, 3, and 5. Really good ones to look at. And 4.7. These are probably not as good as ones in the textbook. These look like some that can be done maybe in a college algebra class. 4 is a pretty good one, but it doesn't seem to have all that much in the way of a practical application. Ones that I really like the best are problems like 5 and 6. Maybe I should, because these don't have solutions, do they? Or maybe it does.
4.6, it doesn't have solutions.
4.6 doesn't have solutions. So that was probably good, and I did this one in class, so you can consider the solution there. I wonder if there's a good one from the textbook that I really like. Of course, the ones in the notes are excellent. Let's see if there's an additional one. Uh-oh. Have they finally taken it all away from me? No, I just have to click on the past. And what?
Resources rather than assignments, possibly.
That could be. Spring. Ebook, there we go. 4 point, where are we?
7.
4.7. 4. 7. Yeah, I think what would be best, I haven't worked through these problems. One kind of like this, I guess I did in class. Example 1, similar to the one I did, one involving the girth of a package and the length. Example 1 looks like a fantastic one. If I could do a problem similar to example 1, I think that would be an excellent test question. Let's see if example 2 looks like it's good. What? That wasn't example 2, was it? Example 2, finding minimum distance. This is kind of like the one I said not to worry so much about. It just doesn't seem as good of a practical application. The minimum area problem looks like it involves, well, not necessarily a quadratic function. No, that's a rational function that's involved. Does that look like a scary problem, finding minimum area there? Rectangular page is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Dimensions of the page. So should it be 8.5 by 11? Will that do it? I don't know. Does that give? That may not do what we need it to do, because we have to have 24 square inches of print, and then margins above and below. This might be a good problem if we had worked it last week. I don't think it's a good problem. Having not looked at it until right now, as far as the class is concerned. Minimum. We did one kind of like we did the, what was it? Laying pipe underneath the ocean versus on the land. And this looks like it could be a similar problem. Good one to practice on. Attached to a single stake here. Running from ground level to the top of each post, where should the stake be placed to use the least amount of wire? You can scoot it this way. It's closer to the top of that, but it makes the Z longer. You can scoot it to the right. It makes the Z shorter, but it makes the Y longer. We'd like X plus Y to be a minimum, and sorry, Y plus Z to be a minimum, and find the value of X that makes that happen. That's a good looking problem. A little bit ugly there toward the end, but it ends up being a polynomial. What's special about X equals 9? Maybe nothing. I actually kind of like that one. Endpoint maximum. 4 feet of wire is to be used to form a square and a circle. So basically take the wire and then snip it somewhere in the middle. And out of one piece of wire, form a square. Out of the other piece of wire, form a circle. What do we want to happen? We would like to enclose a maximum total area. Basically take the area of the square that we form and the area of the circle that we form, add them together, and have that to be a maximum. At what point, how far from the end should we snip it in order for the sum of the two areas to be a maximum? And my guess would be, don't snip it in the middle, but use all of it for the circle. But I don't know exactly how it ends up. Yeah, that's how it ends up. All the wire is used for the circle. So I just spoiled it. Sorry. But something like that looks like a good example. What else?
There's going to be an example like that on a test. There's going to be a formula provided.
Yeah. Well, basic formulas like areas of circle and areas of square, if you need that. Don't care for that one. Maximum revenue, exponential function. This would be nice, maybe for a business calculus course. Just want to make sure that I'm not leaving out any classic problems here. There's the whole, what if cows can swim problem. Maximizing volume. Problem 23 looks like a great one. I put a star by 23, but it's similar to others that we've looked at. 24 looks like a good one. 23 and 24. Yeah, no solutions. There's the drawback. What about 39? Does 39 look good? A solid is formed by adjoining two hemispheres to the end of a right circular cylinder. Oh, we went there and did that, huh? That's probably not a good one.
No.
What about 41? The sum of the perimeters of an equilateral triangle and a square is 10. Find the dimensions of the triangle and the square that produce the minimum total area. What do you think?
I'll see why not. It's just like
What do you think? Sum of the perimeters of an equilateral triangle and a square is 10. Equilateral triangle. So what do we have? S, S, and S, and a square. I guess I need something else other than S.
W.
W. W, W, W. So 3S plus 4W equals 10. Find the dimensions of the triangle and the square that produce a minimum total area. So the area equals area of the equilateral triangle. When I was, I don't know, how old are you in 10th grade?
Wasn't it width times height
16.
divided by 2?
Mine's easy to remember because I was in 10th grade in 2010.
16?
11th grade.
16 maybe? 15 or 16? Yeah, at such time I memorized a formula that expressed the area of an equilateral triangle in terms of the side length. But it's been a long time. So I would have to say 1/2 base times height. 1/2 base times height. Well, the base is S. The height, I think, is 1/2 S times the square root of 3. Based on this 30, no. Based on this 30, 60, 90 right triangle, where you take the length of the shorter side and multiply by the square root of 3 to come up with the height. That's the area of the right triangle. Sorry.
I think you have another S
Of
in
the-
there.
What?
No, it's supposed to be an S in the second one.
Yeah. Plus W squared. So that's the total area of the two. Area equals S squared over 4 times the square root of 3 plus W squared. And then you just have to decide. This is the function this is the quantity that you want to minimize. Would you rather work with S or W? Like W better? If you want to work with W, then to eliminate the S, say S equals 10 minus 4W over 3, and then substitute 10 minus 4W over 3 for S, and minimize that function on an interval that makes sense. An interval that makes sense. How large? If the sum of the perimeters is going to be 10, then W better not be more than 1/4 of 10, huh? So W's got to be between 2.5 and 0. If W is more than 2.5, that's more than a perimeter of 10, based on this constraint that we have. So with that interval of acceptable values of W, you can come up with a minimum value of this. If you can find a way, it's a polynomial. It's an ugly polynomial, but it's a polynomial. If you can simplify that, take a derivative, set it equal to 0, find a critical number, I think you could find a nice minimum value. I kind of like this problem. I don't know exactly how it works out. I probably ought to work it out before I give it to you to work. But it looks like a nice one. Any other nice ones? And at least in the book, probably there's an answer. It may not be a solution, but an answer. if that's enough said about this section. Projectile range, minimum length, minimum time. I think that's probably enough. 4.8. What to do with these differentials? We did one like one in class. That's certainly going to look at. Volume of the right circular cylinder. We have to calculate the differential of the formula for the volume of a right circular cylinder in terms of C. We did that one in class, so definitely that's a good one. And it walks us step by step through the process, calculating the maximum percentage error in the measurement of circumference, maximum percentage error in the measured value of the height, and the estimated maximum percentage error in the calculation of the volume. We did basically that exact problem in class. How'd you feel about problem 2?
And those formulas would be provided.
What's that? Yes, the formula. If I wanted it in terms of the circumference, I could simply give it to you in terms of the radius length and the height. Measuring the radius length would be a little tricky, but I guess if you knew exactly where the center was, it wouldn't be all that bad. Okay. I would say let's not worry about. I think that's plenty for this next test. I mean, what we can do from my guess is the final test that we have will be the majority of Chapter 5, and at some point we'll have to cut that off, and then the final exam will include everything, but in particular, it will include some problems from the end of Chapter 5 that were not addressed on our final regular semester test. That's the way I'm seeing this. All right. Let's finish up 5.1. Did that talked about some basic definitions there, and did we do example 3? We may not have. Let's look at example 3 from 5.1.
We only did example 2.
Okay. So section 5.1, evaluate each integral. Now in each of these we're going to use the so-called power rule for integrals or power rule for computing antiderivatives. See if I'm careful with the details here. If we want the integral of x to the power of m dx, I need for m not to be equal to -1. That's going to cause a problem for us because we're going to need to divide by m plus 1. If m equals -1, then m plus 1 equals 0, and we cannot divide by 0. So I need to exclude the case that m equals -1. It will be dealt with separately. But if m is not equal to -1, what we would do, talked about this last time, if we're taking the derivative, we would first multiply by m, and then subtract 1 from the exponent. We've got to reverse those operations in reverse order. the opposite of subtracting 1 from the exponent is adding 1 to the exponent. The opposite of multiplying by the exponent is dividing by the exponent. And of course, we need a constant of integration. If we find an expression whose derivative is equal to the original, then adding any constant is also going to have a derivative equal to the original. So we must have the constant of integration. Basically, this represents the set of all expressions whose derivatives are equal to the integrand x to the n. So the first one is laid out exactly what we need. We would add 1 to the exponent and then divide by that new exponent that we got and then add the constant of integration. So it's going to be 1/6 times x to the 6th plus c. And usually it's going to be easier to check our answer than it is to find our answer. If we can quickly calculate the derivative, we would take 6 and multiply by 1/6, then get 6/6 or 1, and then subtract 1 from the 6 to get 5. So it's pretty easy to check that the derivative of this, regardless of what c is x to the 5th.
Thank you.
Go. The second one. Well, we don't have an expression where we have x to the power of m in the numerator. If it's a fraction, it needs to be in the numerator. If it's not a fraction, well, let me just say this. If it's a fraction, it needs to be in the numerator. If it's not a fraction, it's not an issue. It is a fraction, but we don't have x to the 3rd power in the numerator. What we need is this, the integral of x to the -3. There. If we have this, then we can apply the power rule. So add 1 to the exponent, and we get x to the -2, and then divide by that new exponent that we just got, and then add c. And then simplify. The 1 over -2 is equal to -1/2. But when we have the x to the -2, that's going to shove that down in the denominator. I can include an extra step. You probably don't need to write this extra step. -1/2 times 1 over x squared plus c, and then multiply those fractions together to get -1 over 2x squared plus c. To check that, we kind of have to undo some of what we've done. Probably you'd want to look at just the first step there and see if you can take the derivative of that, multiply the -2 by the -1/2 to get 1, subtract 1 from the exponent to get -3, and then shove it down the denominator and call it 1 over x cubed. The last one, x to the 2/3, add 1 to the exponent, x to the whatever 2/3 plus 1 is, and then divide by whatever 2/3 plus 1 is. Tack on the constant of integration plus c. So this is going to be, well, let's figure out what 2/3 plus 1 is. 2/3 plus 3/3 is how many thirds? 5/3. So we're actually dividing by 5/3, and that's equivalent to multiplying by 3/5. So this is 3/5 x to the 5/3. Hang on to that constant of integration all the way down. Looks like this. If we were to multiply the 5/3 by the 3/5, we'd get 1. And then if we subtract 1 from the exponent, we'd get 2/3. So 1x to the 2/3 would be the derivative of this, and that's what we want to happen. Are these hard problems or easy problems? Easy problems, good. Properties of the indefinite integral. It's a linear operation. Integration, just like differentiation, is a linear operation. Basically, if we apply it to the sum of two expressions, then it's equivalent to applying it to the individual expressions and then adding those two results. Likewise, the integral of a constant times a function is equal to the constant times the integral of that function. So just kind of a quick note, the integral of a sum is equal to the sum of the integrals, and the integral of the difference is equal to the difference of the integrals. In the next couple of cases, I'm really going to emphasize these properties to kind of an extreme extent that we wouldn't do in regular practice, but just want to emphasize that we are relying on these properties in order to say what we'll say about integration, but eventually we'll just take these properties for granted and we won't show all the details because it can be a real pain. So the first one, we use property A, the integral of a constant times a function is equal to that constant times the integral of the function. So step one, we can take the 3 that's inside the integrand and pass it through the integral. Just like we could do if we're taking a derivative. We could pass the 3 in front of the ddx. So this equals 3 times the integral of sine x dx. So we don't have to stop and think, I wonder what we could take the derivative of to get 3 sine x. We just have to stop and think and ask ourselves, I wonder what we could take the derivative of to get sine x. So what can we take the derivative of to get sine x? Negative cosine x. If we take the derivative of negative cosine x, ddx of negative cosine x equals sine x. Yes, it does. It's the negative of the negative sine x. So it's sine x. So it's going to be 3 times. So I'll put a big set of brackets or parentheses. Maybe parentheses. Negative cosine x plus c sub 1. So I put a constant of integration there, and there are going to be a couple different constants of integration in this problem, so I'll denote the first one that I run across as c sub 1. Of course, we would want to distribute the 3 across the parentheses. There's no need to leave this in parentheses like this. So I'm going to say this is negative 3 cosine x plus 3 c sub 1. But the thing is, 3c sub 1 represents an arbitrary constant. And it's kind of silly just to say 3c sub 1 could be anything. It would be better just to rename it, call it c, let, off in the margin, let c equal 3c sub 1, and just say negative 3 cosine x plus c. So, take the derivative of negative 3 cosine x plus any constant, and you get 3 sine x. That's what we're saying. In practice, we don't have to, if we know what we're doing, we don't have to think so hard about the 3c sub 1. Now, there's some situations where it's kind of important to know exactly where the constant integration should go at each stage in the process. So if there's any doubt, probably do want to go through and really emphasize that this is where it is, but we're going to go with it just like that. Next, we're going to do a combination of things. Well, maybe just the last one. The integral of the difference equals the difference of the integrals. I'm going to take for granted the constant times the integral and just apply the power rule as though it's okay to use a constant in front of it. I'll save this a little bit of time. The integral of the difference is equal to the difference of the integrals. The integral of 3x to the 5th dx minus the integral of 2x to the 4th dx. Separate the two integrands. Because I can't apply the power rule to either one of them individually because, we can't apply the power rule to that difference because that's not x raised to a power. But we can apply the power rule to them separately. I'm wondering to myself, Do I want to take the 3 out in front? Do I want to take the 2 out in front? Or do I just want to say 3x to the 6th and divide by 6? I think I'm just going to say 3x to the 6th and divide by 6. So here goes. 3x to the 6th over 6 plus c sub 1 minus 2x to the 5th over 5 plus c sub 2. If you watch the video on this one, I may have done it differently in a previous semester. I may have gone ahead and taken the 3 out in front, taken the 2 out in front, and I would have found myself dealing with a 3c sub 1 and a 2c sub 2, kind of like in the previous example. But it won't be long before we've done enough of these where we realize it's not something we technically have to do. This is 1/2 x to the 6th plus c sub 1 minus 2/5 x to the 5th minus c sub 2. So let c equals c sub 1 minus c sub 2. And what do we have? 1/2 x to the 6th minus 2/5 x to the 5th plus c. So when we boil this down, we just need any old expression that we can take the derivative of and get 3x to the 5th minus 2x to the 4th. Anything will work. If we take the derivative of 1/2 x to the 6th, we get 3x to the 5th. If we take the derivative of negative 2/5 x to the 5th, we get negative 2x to the 4th. So if we take the derivative of 1/2 x to the 6th minus 2/5 x to the 5th, we get the integrand that we want. Tack on any constant of integration, and we're good. The process, it just says we can use these rules. The integral of the sum is equal to the sum of the integrals. The integral of the difference is equal to the difference of the integrals. And so we can integrate term by term, just like we can differentiate term by term. And it greatly expands the scope, the kinds of functions we can integrate. Might have to use a little bit of trickery here to get at these. The integral of, the A part, there's something I've not told you, but I think we have enough information to get this done, and probably I did this deliberately. It's going to be the integral of 3t over t squared plus 7t cubed over t squared dt. Basically, taking that fraction, noticing that we have a monomial in the denominator. If it's a binomial in the denominator, it's just going to be ugly, and there might not be a real nice way to get around this. But just a monomial in the denominator, involving that variable, we can break it apart and write it as the sum of two fractions and reduce those individual fractions and come up with separate expressions that we can integrate term by term. First one is going to be the integral of 3 over t. The other one is going to be the integral of 7t. So the integral of 3 over t dt plus the integral of 7t dt. Well, here's the thing. 3 over t, that's like 3t to the negative 1. And we said that if we're applying this power rule, where did I say it? Right there. The exponent's not allowed to be negative 1. That's a problem. That's a problem. The exponent is negative 1. So what we'd have to think about is what we could take the derivative of to get t to the negative 1, or what we could take the derivative of to get 1 over t. And it's not a polynomial. It's not a rational expression. What very important function have we taken the derivative of at some point in this course and gotten 1 over t as the answer?
Natural log.
Is it the natural log? Derivative of natural log? Yes, 1 over that expression. So let's stare this down and see if this would not be 3 times the natural log. Now I could say the natural log of t, just plain old t there, but actually I think we went beyond that and said not only was it true that ddx of the natural log of x is equal to 1 over x, but we doubled the domain. Remember when we doubled the domain? We said not only that, but actually the derivative of the natural log of the absolute value of x is equal to 1 over x. It works on an interval where x is positive. It also works on an interval where x is negative. For this antiderivative, we'd like to do it for as much of the domain of 3 over t as we can. We'd like it to apply when t is positive. We'd like it to apply when t is negative. So we put absolute value bars. Because whether t is an interval where t is positive or it's an interval where t is negative, if we take the derivative of 3 times the natural log of the absolute value of t, we'll get 3 over t. We don't need absolute value in the integrand, but we can put absolute value in this antiderivative, and it'll double the domain without costing us anything. Plus, now here, the exponent is not negative 1, it's positive 1. So we add 1 to the exponent and divide by the new exponent that we get. 7t squared over 2. And notice I've already begun to be cavalier with my use of the constant of integration. Technically, I should probably put a plus c sub 1 after this first one, and a plus c sub 2 after the second one, and let c equal c sub 1 plus c sub 2. But I'm just going to say plus c.
Why isn't 7t cubed?
Well, because we've got a 1 there. Oh, which one is not 7t cubed?
The one on the bottom.
The one on the bottom?
Well, both of those, I guess.
Because I'm just adding 1 to the 1. Just adding 1 to the 1. So it'll be squared.
And then A on the top left.
A on the top left, this one?
Yeah.
Well, it's just this 3 minus this 2.
Yeah.
Gave us a t to the first power to work with.
Oh, okay. Forgot we were simplifying those.
So this will work. The B part simply involves trickery. There's no really good suggestion. There's probably other ways of approaching this, maybe some way more complicated ways. But the 1 plus cosine x, it's really kind of tough dealing with these when there's a binomial expression, multiple term expression in the denominator. If there's some trickery that'll work, then I would suggest doing it. So, anybody know what I'm about to do here?
That's your identity?
Well, kind of, yeah. Basically, we want to use the Pythagorean identity, and we can get at that Pythagorean identity with something like this. We could write this in terms of the 1 minus cosine squared x. That would give us the single expression sine squared x in the denominator. And so once we get that, then maybe we could rewrite this like we did the previous one. If we have 2 terms in the numerator and just 1 in the denominator, we can write it as the sum or maybe difference of a couple of fractions, and then deal with those individual fractions. But with multiple terms in the denominator, it's beyond the scope of Calc 1. There'll be different techniques in Calc 2 for dealing with that sort of situation, but it's really beyond the scope of what we do here. Integral of 1 minus cosine x over, okay, we know it's going to be 1 minus cosine squared x. And we know that's going to be sine squared x. So I'm going to skip that step and just say sine squared x right there, dx. Let's see if there's hope for taking this and writing it as the difference of 2 separate fractions. The integral of 1 over sine squared x minus cosine x over sine squared x dx. Okay, if you just ask me, I'm not going to have any idea what we can take the derivative of to get 1 over sine squared x, but I might be able to think of it and figure out what we might be able to take the derivative of to come up with cosecant squared x. That looks more like something on our list of derivatives of the half dozen trig functions. And for this other one, let's see, cosine x over sine squared x, if that could be written as, what do I want there? Does cosine x over sine x times 1 over sine x help?
Cotangent is negative cosecant squared.
I think this could work. Cotangent, oh, so for the first one, got the wheels turning on that one, that could be cotangent x, or maybe negative cotangent x. Someone would have to work out the sign somehow, SIGN. The second one, I'm going to say this is weird, but humor me here. Negative 1 times negative cosecant squared x minus or plus negative cotangent x cosecant x dx. Have I successfully spoiled the problem for you now? I just want the next step to be as clean and neat as possible. I suppose in real life, even math is never this clean and neat. We should just rough it out here. What can you take the derivative of and get negative cosecant squared x? What was it, Patrick?
Oh, negative cosecant. Oh, cotangent or negative cotangent.
So it's going to be negative cotangent x.
Oh, to get the negative cosecant?
Yes, so just plain old cotangent x.
Plain
Plain old cotangent x. What can you take the derivative of to get negative? I think the way we said it was it negative cosecant x cotangent x?
Yeah.
We memorized it? I think that is the derivative of cosecant x. So maybe the cleanest, neatest way to write this would be cosecant x minus cotangent x plus c. It would take a little bit of work to take the derivative of this and try to make it look like 1 over 1 plus cosine x. More work than we have time for right now. It's a good time for a break. I think there might be a good GeoGebra example here. Let me take a moment and think about it. All right, when you look at your list of things to do, courses to take in your mathematical future, who has differential equations on your list of things to do? Whoa, bunch of folks, okay. And those who's happy that differential equations is not on your list of things to do. All right. All right, good. Basically, what we're looking for here, we're trying to solve this differential equation. The derivative is given f prime of x, and we're looking for the function that will satisfy this equation in which a derivative is involved. So it's not one of the more challenging differential equations that one might run into, but strictly speaking, it is a differential equation. A general solution would be the set of such functions that may satisfy this. A particular solution would be, any one solution, but we want the particular solution that satisfies this initial condition, kind of a starting point where we have a specified value for the function that we're looking for at a particular number in its domain. So if f prime of x equals 3x squared minus 4, we could do it something like this. The integral of f prime of x dx equals the integral of 3x squared minus 4 dx. Basically integrate both sides with respect to x. When we do this, a function, an antiderivative would be a function whose derivative is f prime. So big F of x is going to be, and I don't need constants of integration on both sides, either side would be fine, is going to be 3x cubed over 3, add 1 to the exponent, divide by the new exponent that we found, minus, 4x, I just ruined the problem for myself, minus 4x plus c. I think I can fix it though in the GeoGebra example. So one more thing, big F of x equals x cubed minus 4x plus c. So any one of these, for any value of c, it's going to satisfy f prime of x equals 3x squared minus 4. Infinite supply of these. We need the one, basically we're looking for the value of c that will give our function a value of 3 at 1. So, not too tough to find, f of 1 equals 1 cubed minus 4 times 1 plus c, and we'd like that to equal 3. What value of c is going to make this happen? It's looking like what? Maybe c equals 6. So if that's the case, f of x equals x cubed minus 4x plus 6. X cubed minus 4x plus 6 is a particular solution. It's the particular solution that satisfies this initial condition. So basically there's a knowledge of what the derivative of the function is, and there's also the knowledge of what the value of the function is at one particular number in its domain. So this is the answer that we want. Now, what I was trying to do during the break is come up with a GeoGebra worksheet that had a lot of different functions that would satisfy that the derivative is 3x squared minus 4. I left off the minus 4x though. I think it's an easy fix. Let me see. It may not be. I might just have to redo this. Let's see. I don't think I can just go in here and edit.
Object properties.
Maybe. I might be able to. What if I put in a, was it minus 4x plus c? There we go. And then for this one, put in a minus 4x. I've got the plus a there. All right, so what I would want is the 1, and let's go ahead and display it. Let's say big F of x equals, what did it call it? Little f, I guess. Little f, and make it large. Make it large. All right. So for the 1, and I maybe should make it the same color as the other one. So the red one is f of x equals x cubed minus 4x plus 1. And if I move this, adding or subtracting a number to the right-hand side is going to be a vertical shift, up or down, depending on what we add or subtract. A lot of functions that have the indicated function as their derivative, but the one we want is apparently not going to show up unless I increase this maybe to at least 6, how about 7? There we go. So if we go up there, the one we want is f of x equals x cubed minus 4x plus 6. So all this family of functions that have that particular quadratic as their derivative are all going to be vertical translations of each other. It's not news, I'm sure you were thinking that. It's kind of interesting, I think, to visualize it though. And let's see if we can do this projectile motion problem where I actually use meters instead of feet. Okay, here goes. Rock is thrown upward from an initial height of 40 meters with an initial velocity of 20 meters per second. using negative 9.8 meters per second squared as the acceleration due to gravity near the surface of the Earth. Find an expression for the height, S of t, of the rock in meters as a function of the time in seconds. So we have A of t equals negative 9.8. I'm going to suppress the units for simplicity. We'll include the units in the final answer. Sometimes I want to include the units because there's some particular significance, and there is kind of. If I miss them, I'll put them back in. But for now, I'm going to suppress them. A of t equals negative 9.8. So V of t equals, well, we take the derivative of the velocity to get the acceleration. The acceleration is the rate at which the velocity is changing with respect to time. We differentiate the velocity to get the acceleration. It would make sense then that we should integrate the acceleration to get the velocity. So V of t equals the integral of A of t dt. So V of t equals the integral of negative 9.8 dt. So V of t equals, have we integrated a constant? Have we done that? What kind of function can you take the derivative of and get a constant?
E of
It would have to have like
e to the power of something.
oh, well, you take the, I see what you're thinking. We take the derivative of e to a power, and what you get is a constant times that expression. I'm just saying in just a plain old constant. What types of functions have constant slope? A line. A line. So a linear function is what we need. So how about negative 9.8 t plus c? Negative 9.8 t plus c. But we can be more specific because we have an initial condition. The initial condition on the velocity, initial velocity of 20 meters per second, what we know is that v of 0, v naught, if you will, is equal to, well, let's do this. For the sake of space, negative 9.8 times 0 plus c, and it's given to be 20 meters per second. That's enough information to solve for c. Basically, 0 plus c equals 20, so c equals 20 meters per second. So finish up the velocity function by saying that with the given initial condition, v of t is negative 9.8 t plus 20, where the velocity will express the, well, v of t expresses the velocity in meters per second. Now, if we have the position function, we can take the derivative of that to get the velocity. The velocity is the rate at which the position is changing with respect to time. So the derivative of the velocity is equal to the, the derivative of the position is equal to the velocity function. It should hopefully make sense that if we integrate the velocity function, we could get the position function. So S of t equals the integral of v of t dt. So S of t equals the integral of negative 9.8 t plus 20 dt. We need a function that we can take the derivative of to get negative 9.8 t plus 20. Power rule, negative 9.8 t squared. Add 1 to that exponent and divide by that new exponent that we got. What can you take the derivative of and get 20? Feel good about 20t there? Plus a constant. Different constant, but a constant. S of 0 equals negative 4.9 times 0 squared plus 20 times 0 plus c, and we're given that what? The initial height, the initial position would be a positive 40 meters. So 0 plus C equals 40 meters. So C equals 40 meters. So S of t equals negative 4.9 t squared plus 20t plus 40. Where if we input the time in seconds, this will give us the position relative to the origin in meters. So basically, if we want to do this in more generality, what we would have is negative 1/2 g. If g is the constant acceleration, 20 would be the v sub 0, the initial velocity, and 40 would be the s sub 0, the initial position. S of t equals negative 1/2, and maybe I should just say a t squared plus v sub 0t plus s sub 0. A function you'll probably come to know and love in physics. Five two. Let's see what needs to be said about sigma notation here before moving on. We're going to work our way toward coming up with an expression for the area under a curve, the area bounded by a continuous, the graph of a continuous function and the x-axis. And we'd like to be able to use integration, ultimately, to be able to do the calculation. In some specific cases, it can be done without having to do integration by using sigma notation and calculating the limit. But let's see if we remember this from pre-calculus. The expression sigma of k cubed from k equals 2 to 6 has various features, and if I can copy and paste this, I can point to them as I describe them. There is the lower limit of summation, which is 2. The upper limit of summation, which is 6. There is the index of summation. I don't know why that was not put in boldface type. The index of summation is k. Typical letters used for the index of summation: I, J, K, M, and N. There might be others that could work, but those, I believe, are by far the most common: I, J, K, M, and N. And, of course, capital Greek letter sigma, denoting that it's the sum. Basically, we take the expression over which we're calculating the sum, and beginning with the lower limit, we substitute that number for the variable. Substitute 2 for k, we evaluate the expression, we get 2 cubed. We substitute 3 for k, we get 3 cubed. Now the increment is 1 each time. Plain vanilla sigma notation. We increment by 1 each time. Increase it to 4, increase it to 5, increase it to 6, and then stop, because 6 is the upper limit of summation. And then the value of the sum is what we get when we crunch all those numbers. Hopefully I did that correctly to get 440 would be the value of that sum. Sigma notation will give us a convenient way of expressing the sum of various either rectangles or trapezoids that we may inscribe in the regions over intervals underneath the curve to be able to calculate or approximate the area bounded by the graph of a continuous function and the x-axis. Practice with these sums. We really do this in pre-calculus a good bit. I don't know if I want to trouble you with these particular calculations. There are other things, trust me, that I will trouble you with. So I don't know if I want to trouble you with those. Properties of sigma notation. Sigma of a constant times an expression is the constant times sigma of the expression. Sigma of a sum equals the sum of the sigmas. But these, I think, are familiar enough where we don't need real specific examples of these. I may not even have to use these summation formulas. We do these in pre-calculus to some extent. There is an example I can think of where we might use one of these, but we may not, so I'm going to keep moving.
Weren't there ways also to plug that into the calculator?
Yes.
Yeah.
Yeah, there are nice ways to do this using the calculator. Evaluating the limit sometimes in terms if there's an unknown here, we might not be able to do that with the T83s and 4s, 84s. Keep moving. Express each sum in closed form. All right. I'm going to paste this and then shrink it down to small print. Thought I was. I want to be able to refer to it. As I draw the picture. What we want to be able to do is this. We want to be able to write an expression for an approximation of the area bounded by the graph of a continuous function and the x-axis over a closed interval, let's say from A to B. So here's A, and here's B. And we're going to say A is equal to x sub 0, and B is equal to x sub n, and we're going to begin by partitioning the interval into intervals of equal size, subintervals of equal size. Ultimately, we'll relax that, where all we need is just a collection of points along the x-axis between A and B, and they don't have to be spaced equally apart. But for now, if I can do this, and it doesn't have to be, well, let's see. Let's see if I can do this so that they look like it's reasonably well done. All right, so this would be x sub 1, and x sub 2, and x sub 3, x sub 4, and eventually we get to x sub n. I guess this would be x sub n minus 1. So what does the curve look like? Well, it could look something like that. And I might as well start at A, huh? Start at A and go over there to B. Could look something like this. And if we wanted the total area bounded by that curve and the x-axis, we don't have a convenient formula from geometry to come up with that calculation. It really depends a lot on the nature of that function. So we divide up into intervals like I've done, and then we approximate the area above each of those intervals using a rectangle. There are other ways to do it. We could use trapezoids, which does a little bit better job, but we use rectangles. So let's see. I would like to choose a point in each of the intervals. So I'm going to pick a point right here. I think for simplicity, it might look good if I choose the midpoints. I don't have to choose the midpoints, but I'm going to do that. I'm going to choose the midpoint here, and I'm going to evaluate the function at that midpoint, and then draw the rectangle that's directly above this interval, like this. And I'm going to choose this midpoint and evaluate the function there, and then draw the rectangle that's directly above that interval. And choose this midpoint, and that gives a rectangle. And let's see, this midpoint, right across like that, that gives a rectangle. And this midpoint, that gives a rectangle. And finally that midpoint, and that gives a rectangle. If we add up the areas of those 1, 2, 3, 4, 5, 6 rectangles, it's likely not going to be exactly the area bounded by the curve and the x-axis, but it should be close. It looks like it should be close because this rectangle, it's going to overestimate it by this much. It's going to underestimate it by that much, and if those aren't far apart, they'll offset each other. And so it should be reasonably close. And there are other ways to do this where they'll miss it by more than that, but I think these midpoints are pretty good. If you look right here, these midpoints that I've chosen, they don't have to be exactly the midpoints. They can be anywhere in those little subintervals. But this first one is called x sub 1 star. And the next one is called x sub 2 star. And so on until the last one is called x sub n star. It's important to know exactly what those values are because we would evaluate the function at those values, and that tells us how high, the function values tells us how high the rectangles are. So the area of any one of those rectangles would be, well, let's say, it's like this. I guess I'll just need to point to it. If I evaluate the function x sub 1 star, it gives the height of this rectangle because that's the height, that's the value of the function there. If I multiply by the length of the interval, I'm going to call that delta x, and that's going to be b minus a divided by n. If they're all the same, then it's the length of the entire interval, that's b minus a, divided by however many there are. If there are 6 of them, it's b minus a divided by 6. So delta x is b minus a divided by n. It's the length of each one of those little subintervals. The height of that rectangle times the width or the length of the little subinterval is going to be the area. If we add that to f of x sub 2 star times delta x and keep doing that until we get to f of x sub n star times delta x, then we could represent the sum of the areas of those n rectangles using sigma notation. Sigma k equals 1 to n of f of x sub k star times delta x. Now if they have constant width, the delta x even could be passed in front of the sigma notation. If that doesn't change as the value of k changes, then we could even bring that in front, but it's ultimately not going to be necessary. We're going to want to allow for the possibility that delta x could depend on k, although it does not in this case. So we do this for one collection of, for one value of n, for n equals 6. And then we think, well, that was a pretty good approximation. How could we come up with a better approximation? If we did it for n equals 6, what might give us a better approximation than n equals 6? Is it possible that n equals 7 or 8 or 9 or 10 might give us a better approximation than n equals 6? If we make the rectangles skinnier, is it possible that if we look at how much we miss it there and how much we miss it there, there'll be less of a disparity between those if the rectangles are skinnier? It turns out to be the case. It turns out that if we evaluate the limit of this expression, if it exists, as n approaches infinity, if it's a continuous function, then this will actually be what we can define to be the area underneath the curve. Let's look at the theorem here. Or actually not theorem, definition. We're going to define the area under the curve as the limit of this expression that we just wrote down there as n approaches positive infinity. Basically take the limit as n approaches infinity, and that's going to be the area. So we would do this in such a way, choose n large enough to give us the amount of precision that we're looking for. Now, we're going to be looking at a way of doing this. We actually have to express this x sub k star in such a way that if we're using a calculating utility to do this, we can actually tell it what's the value of x sub k star if k equals 1. What's the value of x sub k star if k equals 2? What's the value of x sub k star if k equals 3? And we could express x sub k star in terms of, well, what information do we need? The left endpoint of the interval, the right hand endpoint of the interval, the value of n, how many subintervals are there, and is it going to be the midpoint of each little subinterval? Is it going to be the left hand endpoint? Is it going to be the right hand endpoint? Let's consider the situation where it would be, I'm looking at our time. Let me just do this. I'm gonna have to come up with expressions next time. We want to be as thoughtful as we can about this, but it's been a while, probably this time last semester, since I've looked at this. But it'll give me an opportunity to look at it so I can think how I might improve on it. I wonder what's the best one. Area under a curve, that's probably the best one. Hope this works. We need to tell it how many intervals. Let me do something that doesn't dip below the x-axis for now. We're just considering one that's above the x-axis. So let's say, what if that's plus 3 would probably do it, huh? Maybe not. Plus 12? No, that's better. Okay. So the function's positive on a closed interval. I need to tell it the endpoints of the interval. So 4 to 10. And then I need to decide, do I want to use the midpoints? Or do I want to use maybe the left endpoints? Or the right endpoints of the interval? And how many little subintervals do I want? Well, GeoGebra actually gives us a pretty good way of telling how this is going to work. A little bit later in the chapter, we'll use an antiderivative to find the exact area. And if we'll believe GeoGebra, the exact total area bounded by the curve of the x-axis is 132 square units. And it looks like it's pretty close for the midpoint approximation. What if we used the left endpoint approximation? If you look and see as we drag it over, if we use the left endpoints to calculate the heights of those rectangles, it's significantly going to underestimate the total area bounded by the curve in the x-axis, because there's nothing to compensate for the fact that each rectangle is completely underneath the curve. 109 versus 32. On the other hand, if we use the right endpoint approximation, it's way going to overestimate, because you look at those rectangles, everything above the curve is too much. But the midpoint approximation, I think, does about as good a job as anything. Now, what happens if we increase the number of rectangles? 6 rectangles here, 3 rectangles, 1 rectangle. Just use 1 rectangle, it's not that great. But if I go the other way and use maybe 21 rectangles, that's pretty close to 132. If we go with what? 41 rectangles, it's even closer to 132. And if we just push the envelope to 100 rectangles, 200 rectangles, I don't know where I put the limit was, 250 rectangles, then when it does the calculation, very little difference between the sum of the areas of all those little rectangles and what calculus would tell us is the exact area. Well, this is doing it the easy way. We'd like to be able to come up with expressions so we can program our calculators to do this, but this is kind of the idea of what we're doing.